pause there. Okay, so what we're going to do is we want to remove the radicals from the denominator. And so the easiest way to do this is we can transform any algebraic expression and retain its value by multiplying it by 1. And so the form of 1 that we're going to use here is the square root of 2 over the square root of 2. And so by doing so, what we get is 1 times the square root of 2 for the numerator, and that's the square root of 2. And then for the denominator, we have the square root of 2 times the square root of 2, which is just 2. And so we've eliminated the radical in the denominator. So instead of 1 over the square root of 2, we have square root of 2 over 2. These are the same values. If you put them in your calculator, you'll get exactly the same value. It's about 0.7071, something like that. Once you get into the trigonometry part of Math 14, square root of 2 over 2 is going to be a really common number that you use. Okay, so we can do this with variables as well. So if we have 1 over the square root of x, we have the square root of x over x by rationalizing it. So this is a fairly straightforward process. All you do is you choose the radical that's in the numerator or in the denominator and multiply that, use that as your ratio of 1, and you multiply your original fraction. Okay, so when we have something like 3/5, we break up the radical into the numerator and the denominator, and then we rationalize the denominator. And so you have, in this case, the square root of 5 is in the denominator, so we have square root of 5 divided by square root of 5. And so by our rules, since we have the square root in both the square root of 3 and the square root of 5, we can multiply the 3 and the 5, and so we get the square root of 15 over 5. And so that's the rationalized version. So it isn't necessarily just removing the denominator and making it, the squared and then putting the radical in the numerator. There's some simplification that may need to go on in the numerator there. Okay, so if we have something like this where we have 8 over 3 times the square root of 18, the thing that you want to do first is you don't want to rationalize until you've fully simplified. Okay, do all your simplification first. It'll still work if you first rationalize, but then you got 2 things to simplify: the numerator and the denominator. Here, by first factoring this, so 18 is 9 times 2, we can see that we get 3 times the square root of 2. 8 over 9 root 2, now it's the root 2 that we want to rationalize. And so we multiply that by the square root of 2 over the square root of 2. And so we get 4 square root of 2 over 9, because the 8 and the 2 cancel, reduce down to 4. And so you get 4 root 2 over 9. Yes, Ketis?
Why wouldn't it be 18?
You could, okay, but then...
Oh,
yeah. I really think it's best if you do it the way that I have on the slide here. Let me do it the other way if you just, forget. Okay, so if we do this, we'll multiply it by root 18 over the square root of 18. And so here we have this, and then we still have to reduce it. So we say 8 times, this is going to be 3 root 2 over 3 times 18. Your 3's cancel, and then this becomes 4/9, so we get 4 root 2 over 9. So we still get the same place. It's just that instead of dealing with a number of factors, I can eliminate some factors early on by first simplifying. So go ahead and simplify entirely until you get to a simplified radical here, and then rationalize, and then you may still have some simplification to do, but like always, dealing with smaller numbers is easier than dealing with the bigger numbers. Okay, I never had to deal with an 18 here other than factoring it. Okay, another example, let's say we have 4 over the square root of x. And so I'm going to separate the numerator and the denominator. Take the square root of 4 to get 2 over the square root of x, and then rationalize the square root of x. And we get 2 square root of x over x then is our solution. Everybody following here? Look like a pretty straightforward process? Okay, so by far you're going to do this mostly with square roots. So let's try a few of these. Yeah. We'll try a few of these as a class, and then we'll go on to what happens when the index isn't 2, when we're taking things like the cube root or the fourth root. Yes?
I just have a question. So root 15 over 5, if the 5 was under a radical, so you say simplify before you rationalize, so would it be possible to simplify?
There's nothing on this particular one. There's no simplification anywhere here. You know, we have root 3 over root 5, and then since both of these are as simple as they get for what they are, you know, one in the numerator, one in the denominator, we rationalize the denominator, and then it comes out simple like that.
And then, like, just for an example, like if that in the answer, if the 5 was under a radical, could you simplify the 15 and the 5?
You could.
Because they're both under radicals.
Exactly.
Oh, okay.
Okay, so let's try a few here. Okay, so there's one that it really benefits you from to simplify early. Now, if you don't simplify early, if you just try and rationalize the square root of 3 or the square root of x cubed over square root of x cubed, it'll still work, but you have to then simplify both radicals in the numerator and the denominator. And here, by simplifying it in the denominator before you rationalize, you only do it once. Okay, how about the last one? Abby, did you get it?
I got square root of 2 over 2x.
Great, okay. All right. Okay, so let's say we have roots with an index that's greater than 2. Now this takes a little bit more thought. When we took the square root of something to rationalize, we're always looking for exponents that are multiples of 2 to simplify. Here what we want to do is we want to get to the denominator being the cube root of x cubed. Okay, so there's your goal. Now we have this cube root of x, so in order to get there, what we're going to have to do is multiply it by the cube root of x squared. Okay, so I put the little 2 in red. So you have to make this so that the denominator actually gets rid of the radical. You see, if I just did the cube root of x, when I multiplied them out, I would get the cube root of x squared, and that wouldn't satisfy what I was trying to do. So I take the cube root of x squared, and then that becomes the cube root of x cubed, and now that cube root goes away, and we just get the cube root of x squared over x. So this is the crucial difference here, is that we have to look at what is the exponent under the radical, and what exponent do we have to use under the radical in our rationalizing factor in order to make that radical go away. Okay, so let's try one like this. Let's say we have 4 over the cube root of 9. Now, what we do is we factor the 9 to see, oh, that's 3 squared. And so in order to rationalize that, we want to multiply that by something to get rid of that radical in the denominator. And so we're going to just use the cube root of 3, because then when we multiply the denominator, we'll have the cube root of 3 cubed, which of course then is 3. And so our solution then, or our simplified version, is 4 root 3 cube root of 3 over 3. Okay, and another example, a little bit more complicated, and I apologize for my small writing here. It's kind of hard sometimes to know what would be visible and not. So we have the cube root of 20x squared over 9y. So here we follow the normal process in simplifying. First thing we do is we split the radical, and then we, actually that went a little too fast, but anyway, if you look at this up to the multiplication dot right here, let's look at what's to the left of it. So the numerator is the cube root of 20x squared, so nothing's really changed there. And I'm factoring the bottom, splitting it up into two different factors. One of them is the cube root of 3 squared, which is the cube root of 9, right? And then the cube root of y, I'm having that separate. So now my rationalizing factor is going to be the cube root of 3 to take care of this cube root of 3 squared. And then, since this is just the cube root of y, I'm going to use cube root of y squared. So then when I multiply this out, I get the cube root of 3 cubed, which just turns out to be 3. And I get the cube root of y cubed, which will just be y. And then, of course, I do that to the numerator to keep the value the same. And so 3 times 20 is 60. And then the y squared appears under this radical, and we're set there. So there's a lot going on in this one. And I hope it illustrates the fact that you have to look at what the exponents are. Now, you don't actually have to write these things separate. You could write this thing as the cube root of 3 squared times y, and then write a single radical here with 3y squared in there. I separated it just to illustrate that we're really doing two different rationalizations at once. One for the coefficient that involves taking the 3 to the first, and then the second one that involves y squared. Yes?
So is the number that you're always trying to get in the denominator 3 root x cubed?
Something cubed, right. So the goal is to make that exponent, the ultimate exponent, match the index.
So are we going to be given indexes that are, say, like 5?
Sure.
And we do the same thing except it's 5.
Right. So if you have the root, and I think in one of the examples, one of the things that for you to try, there's one like that.
Oh, okay.
And if not, I'll add one. Okay. All right. Any questions on these? Y'all caught up on the notes? All right. Let's do a few more examples here. So notice this is the cube root again. So I'm going to first simplify. And so I'm going to factor everything. I'm going to simplify the numerator, and there's a potential for simplifying the numerator, but the denominator, see, I have 5 to the first, so I'm going to use 5 squared here. I have z squared, so I'm going to use just z here, and then I'm going to multiply that in with everything else that I have. And then I'm going to end up with so along the way, when I'm rewriting the numerator, I'm going to take out the fact that I have 3 cubed, and so I get a 3 as a coefficient. I have x to the 6th, so the cube root of x to the 6th is going to be x squared. I have a y cubed, so that just comes right out of the cube root. And then so what I have left over is the cube root of 2 times, and then my rationalizing factors 5 squared z, and that all ends up over 5z. And so to write that ultimately, I take 5 squared times 2 and get 50, and so I'm left with this. 3x squared y times the cube root of 50z over 5z. let's take another one now. Or actually, let's have you try this one. 6 over the cube root of 32. Okay, so those are the first two. How about this last one? This last one is pretty complicated. Okay, so let's look at what we need to do here. If we factor everything, we look at, we know we're going to be able to, once we separate the cube root of 3 in the numerator and the denominator, we know we're going to be able to take out a y, and we're going to be able to take out a z squared. And then in the denominator, it looks like we'll be able to reduce that power of 2 and that x to the 5th. So let's first separate them and factor, and then simplify the numerator and the denominator separately. So we can take out the y, the 3 remains, we're going to have a y left over, and then we take out z to the 6th, which is going to be z squared. And then in the denominator, we can take out a 2 to the 4th, we can take out a 2 cubed, which will leave 1 2 inside of the radical, and then we can, in x to the 5th, we can take out the x and have x squared left over. So if we then rationalize it, and our rationalizing factor then becomes, since this 2 here is 2 to the 1st, we want to multiply use our rationalizing factor as 2 squared, and since this is x squared, we want to use x. So we have 2 squared x under the cube root of 3, and we multiply that both in the numerator and the denominator, and we get this business here. So then we have to think about is 12, well, 2 squared times 3, can't take the cube root of that, so that's fine. That's going to be 12xy over 4x squared, and we're good. Now, if you notice in the, let me see, here we don't have the issue. You think about the denominators, and notice none of these problems require us to use an absolute value. The first one, our domain is already, of x is already restricted to, or the domain of the expression, we already restrict x to something that's non-negative, so we don't worry about that. The second one, the same thing, even though you know, we simplify an x outside of the 4th root, we still have the x inside the 4th root, so a negative x, if x is less than 0, that's not going to work. And then in the last case, we have a cube root, so we don't ever worry about cube roots because negatives just propagate through the way you would expect it. Okay. Okay. Everybody good with this? Yes.
How did you choose? I understand why you chose x to multiply it by to get it to 3x cubed. But why did you choose 2 squared?
Because we only have 2 to the 1st here.
And you want to get the 2's and the x's both
Yeah,
to the cube?
we want to be able to eliminate it completely, because if we only use a 2 instead of a, we would still have the cube root of 2 squared.
And it would be under a radical.
Right.
Then.
Yes. Abby?
I split 16 into 4 squared and then multiplied it by a cubed root of 4x. Is that okay?
Well, then you have to simplify. Ultimately, when you simplify, do you get the 4 in the denominator like this? Yeah, then you're okay.
How about this big square at the end? With the denominator?
Well, I have an x here that I got from initially simplifying, and then I get the other x from the rationalizing process. All right, so that's all about rationalization. Okay, so adding and subtracting radical expressions. So this is a whole lot like adding polynomial expressions, where we want to add like radicals. Same thing when we have terms that we're adding, you know, we always add like terms, like we can add an x squared to a 2x squared, but we can't add an x squared to an x. Well, you can't add it, there's just no simplification that's possible. We're going to do essentially the same process with addition, with radicals. So, like radicals, the first line where I have 2 root 2, 3 root 2, just the root 2, or negative 7 root 2, those are all like radicals because they all have the same radical. Same thing with the second one. I have the cube root of 3 in each of those with some coefficient on there, so we're going to call those like radicals as well. So when we add them, what we're going to do is do this exactly like we did like terms and polynomials. We're going to add the coefficients of them. So the square root of 2 plus 3 times the square root of 2 is 4 square root of 2. Or if we're going to take, let's say, a mixed bag here, we have the square root of 3, 4 square root of 2, 7 square root of 3, minus the square root of 2, we can only combine the square root of 3 with 7 square root of 3 to get 8 square root of 3, and then we have 4 square root of 2 minus the square root of 2, which gives us 3 times the square root of 2. So we're just adding like radicals. This should feel very much like adding like terms. So the key to all this is to simplify before adding. If we just had radicals that were already in their simplified form, the process is easy. Sometimes what you have to do, though, is simplify to get things working. Like the square root of 20 plus the square root of 45. Those don't really add together, right? Because they have a different number inside the radical sign. But if we simplify these, we know that these factor is 2 squared times 5 is 20, and 3 squared times 5 is 45. So if we simplify those to make it 2 square root of 5 plus 3 square root of 5, we get 5 square root of 5. And so that is simple. And so the process always is simplify your terms before you attempt to add them. Okay, everybody up with me here? Okay. Okay, so let's move on here. Also, just to remind you, all these things are posted at usually mid-afternoon or so. So if you're not sure that you got everything on the charts, you can compare your notes to my charts a little bit later today. Okay, so let's go through a couple examples. So here's one that's just a whole bunch of like terms. We have 2 root 2, 5 root 2 minus square root of 2 plus 3 square root of 2. So here we'll just add 2 and 5, subtract 1 and add 3 to get 9 root 2. Okay, those are all like radicals. Okay, so now we have a mix. We have the square root of x and the square root of 2, so we can combine the ones that have coefficients, or we can combine the coefficients of the square root of x, and we can combine the coefficients of the square root of 2 to get 4 times the square root of x plus 3 root 2. Okay, so now we have 8 times the square root of 27 minus 3 root 3. So the process, of course, first is to simplify. And you ask yourselves, well, the square root of 3 is simplified, but the square root of 27 is definitely not. So 27 is 3 cubed, and so we can take out a 3 squared there. And so we have 24 root 3 minus 3 root 3, and that comes out as then 21 root 3. All right, so we'll throw in some things here. 25y, square root of 25y plus the square root of 64y works out to 25 is a perfect square, so is 64. So we get 5 root y plus 8 root y equals 13 root y. Okay, another one is 8 square root of x cubed plus x square root of 81x. So there's lots of simplifying we can do there. We get 8x square root of x plus 9x square root of x. And notice the x square root of x is common to both, so we just have to add the 8 and the 9 to get 17x times the square root of x. And, oops, I know you're not done. All right, so at this point, probably a good time for you to try some. Everybody caught up on the notes here? All right, so here's a few for you to try and see how you do here. Okay, so any questions on these? Look good? Okay, so like I said, the notes are posted, so if you haven't got everything down, you can get those online. Okay, here's a few more examples, and they're a little bit more complicated. So here we have the cube root of 54y to the fifth, and 4 times the cube root of 2y squared, and we get, by factoring, we simplify them first, and then we notice we have a common root 3 2y squared, and what I want to do here is add the 3y plus the 4, so what I'm going to get then is, just in parentheses, 3y plus 4 times the cube root of 2y squared. Now there's, I guess realistically, when we talk about simplifying, we generally talk about expanding parentheses, right? Eliminating parentheses and writing it in some sort of unique way. And so you think, gosh, going from step 2 to step 3 almost looks like you're factoring it rather than simplifying it. And that's, to a certain extent, true, that that's more or less factoring because you're taking out that common radical. But think about it from a computation standpoint. If you were to, plug these numbers into a calculator, let's say you had a value for y, the second or the last one would be a little easier because you're only using y twice, rather than on the second one you would be using y 3 times. So you probably save yourself some calculator strokes if you're really using this from a practical sense. So in this regard, simplifying just means making it a little bit more compact and readable and easier to calculate, not necessarily strictly a rule of eliminating all parentheses. Okay, so we have the last example for today then. We have the 4th root of 48 times 4 minus the 4th root of 243. Now 243 doesn't necessarily jump out at you as being the 4th root of anything, so you just basically have to factor. Okay, so we factor 48, and there we get 2 to the 4th times 3, and then we factor 243, and so what we get is 3 to the 5th. And so we can write that in the factored form and then simplify those radicals. And we see we have an 8 4th root of 3 minus 3 4th root of 3. And that combines to 5 times the 4th root of 3.